we ended lecture last time by writing the code to add to a tree, a binary search tree. We had a class called tree set that we were writing. And in the tree set, we wrote this add method. I'm going to pop up the code again here. And the problem with it was that it didn't do anything. This is what we wrote. And just remember the general pattern here, right? You have a method which immediately calls a helper, and the helper takes the same parameters plus a node of where in the tree I'm going to process, right? That's the pattern on all these tree methods that we write. And here, what we did was, well, if the thing I'm adding is smaller, go to the left. If the thing that I'm adding is larger, go to the right. Those are the recursive calls. When I get to the bottom, down to a null, I'm going to add the new node into the tree there. Okay? And where we were sort of ending up last time was that it didn't actually work. So if I jump to, sorry, where am I? Here. What happens is that we get to the point in the code where we walk all the way down to the bottom of the tree, and we make a recursive call. Like I think we're adding, what, 45 in this example? So it would go right here to the right of 42. And on the second to last call of add, we say node.data, which is 42, it's less than the value I'm adding. So I'm going to go to the right. Right, that's the bottom branch of the code right there. So I go to the right. I call add on node right with this value. And node right is null. So on the next call, node itself is null. And that means null doesn't point to anything in the tree. And then we say, I don't want it to be null anymore. I want it to be a new tree node that stores the value. And so what happens is we have this variable node that now points to this new thing with a 45 in it. And that 45 is not in any way attached to the tree. And this is where we kind of stopped last time. Now, I don't know. I think for a lot of students, it's kind of hard to understand why that didn't work or what's wrong with that. But I guess what I need you to understand is, like, if you have a pointer and the value of that pointer is null, and you change the pointer to point to something else, that doesn't necessarily affect your tree. If you really want to affect the tree, you probably have to say root equals something, or you have to say some existing nodes left or right equals something. Those are ways that you would be able to change an existing tree. If you make up some other pointer that's not related to the tree, like node, and you set that equal to something, that doesn't really have anything to do with the tree that we're looking at. So how do I fix this? Well, remind me, how do we fix these kind of issues with linked lists if we want to actually make change in a linked list? What's the trick to adding and removing from there? What's that? Yes?
James Bond trick, if you stop one train car earlier.
Go back by one train car. James Bond stops on the previous car so he can, yeah, that sort of business, right? Okay, so maybe that's what we should do here. Maybe we should do the same thing. So what we probably want to do is we'll say, well, okay, if my value is less than, or excuse me, if the value I'm adding is less than the data, I kind of want to go left. But what if there isn't anything to the left? If there's nothing to my left, that means that that's where the new node should go, right? So maybe you'd say something like, if node left is null, then I'll make node left become a new tree node that stores this value. Otherwise, if the node left isn't null, we'll just go that way looking. Sorry, when I give the tree lectures, I always have to remind myself that that way is left for you guys, right? So I'm going to go to the left over there, and maybe I'll add the new thing in my subtree by making a recursive call, right? So this would probably get around the bug, I think. And I could do something very similar here with the right case. If node right is null, then I'm going to put it here by saying node right is a new tree node that stores this value. And if the node right isn't null, then I'll do a recursive call. So I think this double patch we just made would fix the problem. And just to maybe validate or verify that, maybe I'll go back to the client that tries to add things, and let me see if it actually did add anything at this point. So I'm trying to add this stuff, which I think is maybe the tree in the slides. 55, 29, 87. I think this is that tree that's in the picture on the slides. So if I run this, it didn't do it. Oh, I'm so sad. What did we do wrong? I thought that was actually going to work, but I still didn't want to code it this way, but let's look for a second. If the value I'm adding is less, and left is a new tree node. I think it looks pretty good. Oh, well, there is one case we haven't handled here. I don't like this business here. So what's happening is when the tree doesn't have anything in it, it's going to not add anything to the tree the first time, because we never say root equals anywhere, right? Do you understand that? Like if I never say root equals, then no one will ever become the root from this code that we've written. So I probably need to, that same kind of patch I applied in 2 other places, I also have to do here. If the root is null, then make the root a new tree node that stores this value. Otherwise, then recursively call on the root. So do you see I made exactly the same kind of a patch in 3 different places. Do you see that I did that? And let me try it again. Now, in linked lists, we often do the same thing, right? We say if it's the front, set front equals this, and else go walk somewhere and set the next equal this. We basically did the same thing, except tree nodes have 2 nexts. They have a left next and a right next. So that's why I had to patch this 3 places, right? Now I run it, and I hope it did actually make the tree. The tree works. So we have written a correct version of the add method now, and I hate it. I hate my own code, and I don't like this solution. The reason I don't like this solution is just because of what we had to do. We had to patch it up in 3 different places for it to work. And it's the same exact kind of patch. If it's null, don't go off the edge, don't go too far, right? And that James Bond business about not going too far, that's very important for linked lists. But in trees, I think actually the opposite is a better intuition. Just keep going. Go all the way there. Go too far. Do it. It's even better. And sometimes we talk about this, actually, where when you're writing recursive code, there's a temptation students have where they don't want to make one more call and go too far. And they want to stay back a little bit from the sort of very most basic base case that they could reach. And we sometimes call that arm's length recursion, because they want their recursive calls to stay back a little from where they should go to. Now, I'm going to take this blob of code that we wrote, these pair of things, and I'm going to copy them and paste them over in some sort of temporary file editor so that we can come back to them later, because I want to do some surgery here. I'm going to put it back. I think if I hold undo, we didn't change anything. I'm just holding undo until it undoes every single thing I just wrote. Puts it back to the broken way. There's a much quicker and, in my opinion, better fix for this problem. It involves changing one character in the code. And that character is to put an ampersand after this pointer. And let me just make sure that that's true. Let me just run it for you. So here for the helper for add, I say ampersand. And then if I compile that and run that, it also totally works. And so it's kind of neat that just one character change did the same effect of all those 3 if-else patches that I had made otherwise, right? And I claim that this new version is better. So let me first try to explain what the heck is it doing, what does this mean? And then I'll try to, I think maybe why it's better will be self-evident because the code is shorter and stuff. But what's happening here is I am making a reference to a pointer.
Excuse me, is there an Erica here on here?
It's okay. If you're watching on video, one of our students was just given a present from her big. That's a thing, apparently, that happens. I just want, my big doesn't give me anything. How come my big doesn't love me? That's what I want to know. Oh, well, maybe next quarter. No worries, Erica, you're okay. What's going on? We made a reference to a pointer. You guys remember references, right? What's the difference between a reference parameter and a regular parameter? Just put those ampersands on there. What's the difference in the behavior that we'll see? Maybe somebody I haven't called yet today. Yes?
You're passing the actual thing, you're passing the actual thing versus a copy of it.
Yeah, I think that's a good way of thinking of it. Like usually when you pass a parameter, you're technically making a copy of whatever it is that you're passing. And so if you change it inside of the function, you're changing the copy. It doesn't change the original. You have to be careful with how you phrase that or how you think of that, because if you pass a pointer, you are passing a copy of the pointer. But if you follow the copy, it will lead you to the same place that the original one led you. So I mean, you could change the thing that's being pointed at by following the copy. But yes, but if you set the pointer to be null, that doesn't set the original pointer to be null, that sort of thing, right? So you have to have that understanding. That's what you said is that you have a copy normally, but if you pass something by reference with an ampersand, you're really passing the real thing. The analogy I sometimes use is like, if you're at the bank and you deposit something and they say, do you want your balance on the receipt, right? And they give you the receipt with the balance on it. Like if you crumpled that up and threw it away, you didn't throw all your money away, right? It's just a copy of it's a copy of how much, I guess, money you have, or a record of how much money you have. Anyway, the reason this tree node didn't work was because it was a copy of the tree nodes in the tree, basically. When I said make node point here to this thing, that's fine. Node is a pointer that points to here, and also this guy's right is a pointer that points to here. So in the program, there are two pointers that point to the same place. And if I make another recursive call on node.left or node.right, then I make node point to nowhere. Now this arrow here goes away. And if I change this arrow to point to a new box, that does not change this arrow here or this arrow here or whatever to point to a new box. So that's an important thing to understand. But if I pass it by reference, if I pass the pointer by reference, then what I'm really saying is node really should be like this pointer. And so if I set node now to equal to point to something, then the part of the tree there that we're interested in will also point to the thing that we make it point to. So when I say node equals a new tree node, it really does go down here and make this thing point to a new tree node storing a 45. And so that one little character makes a really big difference here. I guess it would raise the question of like, well, why didn't we do that with linked list then? Like, did we do ampersand and linked list? But I think what you'll find is that it's not quite the same bug. You can't fix linked lists and make them easy by adding an ampersand. The reason this is tricky is because of recursion and parameters, and we don't have recursion and parameters with linked list. Like, you still have to be backed by one to set the appropriate next pointer on the linked list. This ampersand thing isn't a panacea for pointer stuff. But anyway, in this context, it works really well. And actually, that's the trick I want you to see here, is that methods that you do on a binary tree that are going to change the tree, that are going to add nodes to it or maybe take away nodes from it, if you're going to be doing modifications like that, you should pass your current position in the tree, your node, as a reference to a pointer, because you might change it. And if you're just going to walk around looking for something like contains or something like that, you don't need to pass a reference to a pointer there, because you're not going to change the tree in that function. Okay? Question? Yeah?
Sorry, okay, so when you hear your node, why is it connected to the tree? I'm sorry. Okay, when you pass it by reference, and you reach the end of the tree, and then if you create, why is it then attached if it didn't start as the root?
Well, okay. I think this is really hard to draw a good picture of, and I will freely admit that this is sort of a mediocre picture at best, basically. But when you have tree node, that's its own. Let's pretend that ampersand isn't here. Okay, that's its own pointer that can point to different stuff. Okay, and at any given call, I can make that pointer equal to some node in the tree. Like I can say, hey, do node.right or do node.left or something like that. And what I'm really saying is, if this is node, if root is the node, and I say call recursively on node.left, I'm saying, hey, this is node.left and it points to here. I want this thing to point to that same place on the next call. So node is its own little pointer variable that happens to point to the same place as one of the left pointer variables in the tree. And the thing that's really important to understand is, if I change this, if I said, I changed my mind and make node equal null, well, I didn't actually modify the tree any. I just cut this this link right here, but this guy still links to the 29 child. I didn't delete the 29 node from the tree by doing that. And by the same token, if node is null, which is what it would be in our previous code, in this code without the ampersand, if node is ever null, why would it get to null? Well, because it used to be here, and then I recursively called, and now it's here, and I recursively call, and now it's here, and I say, this node's data is less than the whatever 45 that I'm adding, so therefore I'm going to make a recursive call on node right. So what that really means is make another call where node is set equal to the same value as this current node's node right. So node right is this pointer right here. So I'm saying, hey, node, you point to the same place as this thing points to. This thing points to nowhere. It points to null. It's nothing. So make another call with node being null, being nothing. It's its own variable that is null, just as this right thing here is null. There's two separate pointers in the program at this instant that are both null. And I say, hey, the node is null. I don't want that to be null. I want it to be a new node. What I do is I change this thing to point to a node storing a 45. But what I really wanted was I wanted to make this right thingy point to the new node of the 45, and it doesn't do that because they're separate copies. Two pointers that both store null have no relationship to each other. Changing one does not change the other. that's kind of what's happening here. I think it's hard to understand, and my pictures only go so far to really explain it. But by making it be a reference to a pointer, when you pass something by reference, you really are passing the thing itself. So if I say node right here, I really am saying make the next call's node be the node right for me. So if on the previous call node is pointing at the 42, then on the next call node is pointing at here, but node really is here. So if I say node equals a new tree node with a value in it, it'll do that. It'll really will change the tree in place rather than a copy of that or something. And I think it's really subtle and hard to understand. And I guess the big takeaway here is even if you have a little trouble understanding the arrows and the stars and the ampersands, I would just say the rule to follow is if I'm changing the tree, if my method's goal is to modify the tree by adding or removing nodes from it and changing what's where, then I need to pass this as a reference to a pointer. That's kind of the big takeaway here. Okay?